Getting the okay, good. Cool. Thanks, everyone. I'm Aman, and this is a joint work done with my collaborators, Shuyan, Uri, Iming, and Graham, and we are all from LTI at CMU. So the title of the talk is Language Models of Code, Our Few Short Common Sense Learners, and let's see what's that's all about. So the kind of problems we want to solve are structured common sense reasoning, right? So we are given something like bake a cake, a scenario, and we want to generate a graph to bake a cake. Each node in the graph is an event. Find recipe, gather ingredients, mix ingredients, preheat oven, and so on, right? So we want to generate a structure. So that's one example. This is from ProScript. And we have other data sets like explanation graph generation, which is, you are given some belief arguments and you want to generate a graph that sort of argues for that or against it. Cool. So that's kind of the kind of problems we are interested in. The expectation is that we have a model that takes this input and gives us a graph. The reality is that pre-trained models are pretty cool. So we actually want to fit our problem to something that can work with pre-trained language models, right? So the reality is that you would flatten this graph into a sequence of edges, strings, and then train a seek-to-seek model that goes from input to output. So that's kind of the paradigm we are all very well aware of. This works. So this works. There's work in the past that has used this to some degree of success. But of course, the problem is that the representations we are working with are not natural, right? So we want to generate graphs. And there are many issues that can happen with converting graphs to strings. And to sort of motivate one of them, you see there's a node called mix ingredients. And, as humans, we can see and tell, yeah, these are the same nodes. But what if, you have a graph that has 100 nodes where the mix ingredient nodes shows up, say, 50 lines apart? Is that still going to be possible with the language model? Is it still going to work? It's kind of up in the air. The main tension here, of course, is that we want to generate structures and not strings. So one solution that we present in this work is that to think about these problems as one of code generation. And that's kind of natural if you think about it. So, programs have all sorts of nice properties about structure, dependencies. For example, one function has to call another function. Classes have functions. Functions can have subfunctions. So there's composition. A variable that you define in the init function in the Python class may appear several times later. So a model that's good at code generation will learn all of these properties. It'll learn hierarchy, composition, copying variables, and so on. Right, so sort of the TLDR of this talk is that we do not want to force language models of text to work on our task. Instead, we want to adapt language models of code into doing something that they are already pretty good at, which is generating structures. So I wanted to sort of cover some background on code generation models. Some of us who have been using Copilot already know what I'm talking about, but for, let's just to be on the same page, let's see what these things are up to these days. They are pretty cool. So for example, in the second case, I literally only wrote the comment, write a program to search Google for a given question, and I just gave it a good function name. Query Google, and I gave a query, and the gray stuff is all generated by my Copilot, right? So it's doing all the imports, import requests, import beautiful soup because, you get HTML that has to be parsed. And it also returns all the links, right? So these things are getting useful. And of course, there's tons of hype. Some of it is kind of, who knows, but, there's something here. It may take our jobs. You can no longer push your kids to coding when they are 3 to save them because there's Copilot. Okay, so we have a very strong LLM of code, Codex. But there's a cool thing. At least if you trust the paper that came with Codex, who knows what's happening now. The model was initialized with GPT-3. So they started with a super strong model of language. And then there's other reasons to believe, the AlphaCode paper, that they can do fairly good at translating natural language instructions to things that actually work. So most of us, or some of us, may know what lead code is. So the first paper essentially says that AlphaCode or Codex-like models can do lead code. Or problems which are, competitive programming. There's a long story about all kinds of nonsense, but you just have to write a DP loop or something like that. And the second paper measures the productivity of programmers and shows that it improves. So, there's actually code that's being used. Okay, so code completion is awesome. So I've sold you on Copilot, but of course the talk is not about Copilot. I do not work for OpenAI yet. So what I'm trying to talk about is, can we leverage these models to do something like, some language-like task? So we want Codex to juggle multiple things. The images were all generated by DALL-E or Stable Diffusion, some of them. Yes, you can. And that's kind of what I show in this work, that you can repurpose Codex to do things about language. It's very simple, right? So all of this was built up, but the idea is pretty simple, or I'm going to keep it very simple. Step number 1, translate whatever you care about, like in this case, common sense graphs, to code. If it's a structure, it's possible. So in this case, we have a class tree. The goal is bake a cake. In the init, we initialize all the nodes. There's a node called find recipe. There's a node gather ingredients, and so on and so forth. And the edges are represented as children attributes of these nodes, right? So find recipe has 2 children, gather ingredients, preheat oven, gather ingredients has 2 children again, and so on. So one thing to note here is that, of course, there's no class node, right? We can just make up something. The trick is to write your structure in a way that you would expect to appear on GitHub or in open source, or in a way people write, right? So it won't really work if you say self x equal to this, self y equal to this, and x has children y and z. The variable names here capture the natural language, and the structure is captured by the children attributes and stuff like that. Okay, so that's step 1. Step 2 is that you create a prompt, or you create some examples, some demonstrations on how to go from input to output. In this case, we create a prompt that has several examples of different structures translated as code. So in this case, the first example is class tree. I've written as the example in the previous slide. And at the test time for a new scenario, we only write class tree. The goal is, in this case, plant herbs in the kitchen garden, def init, and the rest of the code is completed by something like Codex, right? So we are tricking Codex into doing a task for us. Codex thinks, or Copilot thinks, or Code GPT thinks that it's doing code generation, but we know secretly that actually we are making it do common sense reasoning, right? It's pretty good at doing code completion. Let it do that. And once it has done it, we can translate whatever you get back and run metrics and see how you're doing. So that's pretty much it. It does pretty well. So in this case, T5XXL was trained, fine-tuned on 3,500 examples. Da Vinci and Codex are models from OpenAI. They were the 002 series models. And Da Vinci is, now we know, trained on top of Codex on more text. And it still underperforms Codex. But the highlight, of course, is that with just 15 examples, we can get a lot done. In fact, we can outperform T5XXL in some cases with only 15 examples. It's not limited to just script generation. In this case, we have ProPara. So the goal is to map each, or to track each entity as different events happen. And in this case, we represent it as composition of functions. So there's a function main, and then each step is a sub-function. And same story. We find that ProPara is actually state-of-the-art in few-shot learning, and on the leaderboard, it would rank 6th. Every other model above it is fine-tuned. And we only used 8 examples. Okay, but why does it work? So let me share some thoughts on why I think it works. There are two theories. The first is that during pre-training, there's lots of data on GitHub that has common sense. So I'm thinking game engines or people writing simulations. I hope not test set of these corpuses, but I hope not. That's one hypothesis. I don't think that's what's happening, or maybe some of it. I think what's happening more likely is that when you train a model to do few short code completion, it has to be better at keeping track of things. It has to be better at not messing up variable names, right? It has to be better in making sure that if you define a function, when the function is being completed, if something useful is available in the context, reuse it. So maybe it's a bit of both. Maybe it's a bit of training set, and maybe training on code actually helps you in doing better few short structure generation. So what next? So one of the things that we explored with this is, now in this case, we generate code, we translate the code back. The code is actually not executed, right? We don't really care about the results, but we show in recent work that you can actually improve some chain of thought like reasoning by translating the explanation to a Python program. And instead of relying on the language model to generate the answer, we just let the language model, in this case, a code generation model, generate the explanation. Then we pass the explanation to a runtime and get the answer. So, and you can do all sorts of stuff. We can include symbolic solvers, image models, right? So the possibilities are endless. And there's more evidence from other cool work happening that I saw recently on event reasoning. People have shown that these models work pretty well. Embodied control, so making a robot go around, you can generate explanations as code. So there's more evidence basically that code generation models are good at reasoning. Okay, so that's my TLDR. If you have a task that you think can be converted to code, you should try it. Codex is still free. And if the link has all the details. Of course, I glossed over some other cool things we did in the paper, like designing different prompts, creating prompts dynamically, and so on. But I think I've captured the gist. So thank you so much.
Thank you, Aman. Any questions from the audience?
Hey, maybe I missed this detail in your talk. For the few short examples, how did you create the Python scripts?
We wrote it manually.
Okay, and how many few short examples did you have?
I think it's like 8 to 15. It depends on the task.
I see. Okay, thanks.
So technically speaking, we wrote a script to translate these to Python. We only designed the layout, right? So we just had to say, okay, each node in the graph is an instance of the node object. And then we can write a script to do this translation. But the format, we decided like what it has to be. And we tried with different formats, yeah.
And you talked about the variable names being representative, and that's also something you had to do manually?
Exactly, and we find that's very useful. So if the variable names are X, Y, Z, like if the code is horrible, if you cannot tell from the code what's happening, it's not going to work at all.
Makes sense, thanks.
You can alleviate some of that by putting in comments, but it's just so much more useful to have good variable names. So that's I guess a life lesson in general.
Thank you. Other questions?
Hi, thank you for the interesting talk. So my question is, does the order of the lines matter like the accuracy? Because like there are a lot of ways to represent the same graph in code. So like, yeah, you can like start from the root or you can start from the node. So I wonder like if you tested on that.
That's a wonderful question. So we only tried, so ProScript is a DAG. So it's a directed acyclic graph, and we list nodes in topological order, starting from the top. But I think if we don't do that, I think it's going to be not as good because it's autoregressive. So it has to condition on what it has seen. That's a good point. Yeah.
Yeah, thank you very much.
Thank you. It's a very good point. Yeah.
We have time for one or two questions.
Thank you for the presentation. Great work. Are there any blind spots from your experience in Codex that you don't want to use in the program when you are doing the coding to make sure that the graph will be created?
Are
Like
there any blind spots?
in Codex
in the-
generation?
Absolutely. So not for the task, not for CocoGen work that I showed today, but for the reasoning work that is a follow-up work where we actually pass this program to a runtime, we saw cases where the generated programs have, say, infinite loops or divide by zero errors. So definitely, I don't think we should just run these programs as is. I think they should be sandboxed. You should have like a virtual machine or a Docker or something that runs them, because I don't think we are at a point where we can guarantee that the generated code is safe, who knows what it's doing. So, and if you're running this on a large test set, we don't really know if it's importing some URL and trying to do some request to some server, right? So I think it's very important if you're running this kind of code to sandbox it. Yeah, but good point. Yeah. So
Thank
that
you.
would be like the faithfulness aspect of code generation in some sense. Yeah.
Thank you. We're running out of time. I can see there are a few questions on Zoom, so Aman, please check them out. Thank you so much. Let's once again thank Aman. All right, now we move to our fourth talk. This talk is about enhancing self-consistency and performance